Earlier this week, I made a video for Pi Day where I used a Raspberry Pi to calculate the number pi to 1,000,000 digits for Pi Day. It was my first YouTube video, and I asked some people, like, so what did you think? The answer was pretty unanimously, it was too long, overly complicated, and sorry I didn't watch it. So I thought it might be worth just to make a little follow-up video to the video from Pi Day, where I attempt to answer the question very simply, what is assembly language? And then just SSH into a Raspberry Pi, open the Nano editor to a blank file, and just take about an hour and use assembly language to see if I could just code a really simple little calculator just to clarify the concepts a little bit. So if you don't like to watch coding, disconnect right now. Otherwise, I'm hopeful it might clarify a little bit about what was going on, or not. I'm not sure, but we'll see how it comes out. Where I would like to start is to have a quick look at the difference between an interpreter and a compiler. And once we're looking at a compiler, I would like to sort of compare that with assembly language. And then I would like to write a really small sort of micro assembly language program that would get some user input, add two numbers together with assembly language, and print the result. I plan not to just like talk about it, but like just open a window and do it for you to see. I'm going to be doing this on a Raspberry Pi 4 with the 64-bit version of the Raspberry Pi OS. Most of the ones they're handing out now are the 32-bit, so you'd have to look around for the 64-bit and burn an SD card. I'll put a link in the show notes down below. So to get started, I would just like to think a little bit about interpretive languages. The two that come to my mind right away are JavaScript, like would be in a web page, and Python. A lot of people are learning Python these days. So if you were to simply just go and run a Python interpreter, like Python 3, when it comes up, it's in interpreter mode right now, and it will just begin interpreting your commands. So you can say x equals 3, y equals 4, print x plus y, and it prints out 7, literally real time as you did it. It isn't something that had to be compiled and saved away somewhere in a separate file. If you wanted to make a file for that, you could add.py. You would put in your, just like you did before, x equals 3, y equals 4, and then you could print x plus y. And when I save that, if I run it, Python 3, add.py, the 7 that comes out here is simply because it's simply, as this file read in, it began parsing these commands out one by one. JavaScript is the same way. If you were to make a file called add.js for JavaScript, you could go let x equals 3, let y equals 4, and in this case you would console.log x plus y. And if I were to save that and then run that, the 7 that comes out here is simply been interpreted. In other words, as this file was read in to the V8 engine, the JavaScript engine, it simply parsed these commands out real time without needing to have some precompiled program. Let's contrast that with assembly language. So I'm going to change folders here, calling this part 1, and actually make a little folder called CDemo. I'm going to just erase everything out of there and start afresh. I was just playing with it a little bit ahead of time. So nothing is in this folder now. If I wanted to write a little C program that would accomplish the same thing, so in this case it would be add.c, we would need a couple of things a little more complicated than just an interpretive language would have. And one of them is C needs a main function in order to hold the sort of main part of the program, and it needs to return with some value back to the operating system. So that would basically be a runnable C program right there. If you wanted to do the simple addition that we had, we have to specify the type of a couple of variables. So we could have an integer x, we could have an integer y, we could have an integer z declared, and then just like before, we could simply say x equals 3, y equals 4, and then we could say if we want z equals x plus y. There's a very simple program here, but I need to print it. So to print it involves two things. One is an integer. You got to figure out how to make that into text. And the second thing is you need to actually output it to something. And so the operating system has taken care of all that in a library. So I come up here and I add include statement, and I want standard io.h. That will tell it to go look in that library for this printf function. And then the variable that I want to print is simply z, but I have to give it a little information on what I want it to print. %d is going to tell it that it is a integer, and then I'm going to put a carriage return at the end of the line just so that we can see it. So this should be a complete runnable program. If I want to make this a little bit bigger here, if I want to compile this for execution, then I need, and I'm just going to put it up here so we can remember it, compile to run. The command for that would be gcc, and then -g means include the any local symbols and things that we have, and then dash my output file -o is just going to be called add, and my input file is add.c. And so this will create an output file add from an input file C and include some debugging information. So if I exit out of here, and again, I can just type my program out to see that it's there. I'm going to compile it and see if there's any errors. There's not. So now I have a new file in here called add, and it has executable permissions, so it's runnable. So if I run that program, I get my 7 out. I say, okay, well, that's fine, but I did have to compile a separate, executable program. There's another thing you can do in the compiler is you can tell it, the GCC compiler, that I want to compile it to assembly language. That's what we're looking at right now. So if I type GCC and then use an uppercase S for assembly language, and then so my output file is going to be add.s, because that's what typically I use on ARM assembly languages file, and my input file is going to be add.c. So then that file should produce an assembly listing. So I'm going to copy that to the clipboard. Let me just put my note on that. So we'll compile to assembly language. So now, where did it go? I need that one. So now I have a new file in here. And this now doesn't look anything like, and I want to kind of put the two side by side. So I have kept a separate little login window over here. So these are my files. So I'm going to cat, that was the wrong one, cdemo. So I'm going to cat that add.c so I can look at it here in the screen next to me. So that particular, I can't grab the bottom of that. This file here, where we have this sort of core functioning in here, these variables would needed to be defined somewhere, and they were actually created on the stack. So offset 28, offset 24, and offset 20 represent a place that these three variables have been assigned. And then up here, I'm just going to look at this instruction, just go straight to it. What would this instruction do to the ARM processor when it gets it? It would say, this is a move instruction, and this is a 32-bit register number 0. So I'm going to move, and they call this the immediate value of 3, into a 32-bit register called W0, and then I am going to store that register, str is store that register. Which one? W0. Where am I going to store it? I'm going to go onto the stack at offset 28, and these brackets mean go to that place in memory, and the store means put this value there. So where we say X is the offset 28, it's going to put the value 3 into it because that's what's in the register. And likewise, 4 goes in here, and that goes into offset 24. And then we do our addition. You can see an add instruction here. So these are some sort of instructions that let us look at the specific steps the processor would do. But the processor is not going to read this file. So there's one more sort of level we can do to this file up here. I apologize for my colors. If we want to compile, I'm going to use the word here, assemble to a object module with listing, then we would do GCC. I'm sorry, AS is the assembler. The other one was a C compiler, but because we've already made assembly language, we're going to use the assembler. So -G means put in the global symbols. My output file is going to be add.o, which is an object module. We're not going to worry about that right now. My input file is add.s. That's the one we created as the output of this one up there. And then at the end here, I'm going to say I want to add a add.lst listing file so I can go look at the actual machine instructions that were generated. So if I'm going to copy this command out of here. So if I execute this command, now I list it. Now I've got one more new file here, and this is, and now I need to move my screens around a little bit here so we can see that. And I'll put this one over the top. So now the code that we were looking at before has now been translated into machine instructions. And the one that would jump out among any others is this addition from over here. If you could see it highlighted on that side, we've got an add instruction. I'm going to narrow this down a little bit so I don't lose it. We've got this add instruction here that corresponds to the plus side. We just went through some of those others. But what we have over here is some places in the code where the actual words are being stored. So we say, well, this is like assembly language, but this is the actual machine code that's going to be in the machine and run to do this add command. You say, well, where do these codes come from? Just take a minute to open because it's a whole lot of pages. Wrong one, sorry. This one. The add commands that are going to come up in this have specifications as to how the bits are made. So I'm going to flip back and forth between a couple of different ones here just to kind of make the connection. So we started from a C program over here. That generated some assembly language in the middle here. And then the assembler brought in some bytecode in order for the processor to process. But the bits on that have various values. And I would like to just digress a brief moment here and pull over my my PowerPoint presentation, is that reminding you that memory up here can be 1 byte, that is 8 bits coming across here, or in hexadecimal, there would be 4 bits per digit, so 0x00 would be 1 byte. You could have 16 bits or 2 bytes, 32 bits as a word, or you could have a full 64-bit word. This is a 64-bit processor, so when it's operating in its full size, it would be doing that. And then the actual bits in hexadecimal would represent some combinations of digit A through 9 and then A, B, C, D, E, F. So over here, if we count these, we have 4 bytes or 8 digits. So that means we're looking at a 32-bit value in memory. And that 32-bit value for the instructions, depending on what instruction you're looking at, and there's a couple of different, adds here. There's add immediate, add shifted registers, and these have different bit codes here that correspond to those. So by looking at, what's in these instructions here, and this particular add here would be 0100, and then you'd have to kind of hop around in here and look a little bit and see if you could match them up. But you'd be able to match up some of the, this would be how the information is made. This is all encapsulated into one 32-bit value, including the instruction and the arguments. And that's why it's a little bit limited. This is a reduced instruction set. If it doesn't confuse you too much, I would like to just open that up. And this is a Raspberry Pi and the ARM processor. I would just like to compare that to an Intel processor. So if I get one more terminal window open up here and I shrink this one down a little bit, I can cat my add.c program out and copy it to the clipboard. And then up here, I can make directory cdemo, and I can go to cdemo, make my text bigger. And then if I nano add.c, I can put this exact same program in there, exactly like it was before. And then if I go up and grab this first line, exactly like before, I can run it. Now I have a runnable file, and I can get my 7 out. But this is on an i7 processor, and this is on an ARM processor with a reduced instruction set. So if I follow these other two commands exactly the same, I can put that in, and this will compile it down to the assembly language. And so now if I do my source file here, this starts to look completely different because these are different names of the instruction sets, because these are the ones Intel uses, and there's a much more complicated register usage because it's a much more larger complex type processor on an i7 chip. But I could go and look at the actual assembly language that it would generate exactly the same, and I come up here and pop that in. Then now a couple things to notice on an Intel processor is I have assembly language here which is doing some of those things, and here's my famous add statement because I had, if I can get my other window open for a minute, close this one down and move my PowerPoint out of the way. I have my add statement here in the equation, so then I've got my add here, but this processor is so complicated that it can do 4 bytes, 5, 6, 7, depending on how big they are, or this is an instruction which is only 2 bytes or 16 bits. So you can see there's a giant flexibility in what this one can do in terms of its complexity. What runs on the microprocessor coming out of the memory is these are being read in out of memory, and the processor is interpreting these based on the bits that are in them like it is in the other one. So we sit there and say, well, that's nice, but why would you bother to do that when you can just do that over here? And in the example, in my case, is I'm trying to calculate pi, the number, on a Raspberry Pi down here, and I think I'm going to close this upper one out. I don't really need that one anymore, to 1,000,000 digits of accuracy. So these are, integer variables here. Depending on the size of the machine, they might be 20 digits, they might be 10 digits, or, however many digits they are. But this depends on the sort of the way the compiler has been written and these predefined variables. But there's not a data type in C that is 1,000,000 digits. And you could say, well, I'll write an array and I'll have lots of things. Yeah, you could do that over here. But if you want to do some mathematics, some arithmetic calculations that aren't the ones that are sort of pre-made in this compiler, then you could go to assembly language and you could just write your own, because then you are the machine. And so let's think about doing that and see where we get to here. So in order to do this, I'm going to make a folder, and I'm going to see what to call it. Let's call this, let's just call it demo. And now I need to start with a assembly language source code file. So, and I'm just going to use nano here, and I'm going to call it add.s, like we did before when we had, up here, just to go on the other one, up on the upper right, we had that sort of source code file that we had add.s. And we need a couple of minimum things for an assembly language program to run. One of them that we need to do is we need to define an entry point called start. And so by putting the name here and the colon after it, that means that's going to define a memory location back in all that hexadecimal stuff. And then because I have defined it for the linker to see it, I need to make it global. And so now I have a label that represents a memory location that is going to be global to the operating system. The other thing that I need to have in here is I need, when I'm all done running, I need to be able to have the program quit and return control back to the operating system. So in order to do that, what we need to do is I'm going to set up a little place here and call it exit to operating system. We're going to use a little assembly language here now, because what we want to do is we want to tell the operating system what a return code would be, like if we had an error. So I'm going to move. You saw me use that command before. I'm not going to go through the detail of what all these commands are. The pound sign means this is an immediate value. I'm going to put 0 in the X register because that is going to be my return code. And then I need to tell the operating system that, like you could, open a file, or you could, read a keyboard or something like that. I'm going to move the X8 register, just a number that's 93. That number 93 means exit requested. And let me comment this one. So this is return code. Like most programs return a code in Unix when they end. And then I need to do a system call, which is, you would enter it here as SVC 0, and it's always that. And this is like, call the operating system. And then the operating system will go forth and do something, and it would hopefully exit the program at that point. So if I want to come out of here and save this, I'm thinking it won't do anything yet, but I should have a runnable program. So I should be able to assemble it with AS for assemble, and then -G means include the globals, -O, and I need to make this kind of intermediary module because the assembler has different modules. So this one is going to be main.o, and then my source code file is going to be main.s. So if I do that, actually I want to call that add. I'm going to call this add.s, and I'm going to call this add.o, I'm sorry, and add.s. And then I want to look at the listing file that I would have just like I did before. So I'm going to call this add.lst. So I've got something not quite right. What do I have here? Oh, what? My add.s -a. Forgot the hyphen. So now that has now made from my source code file, which is add.s, which is just the exit to the operating system command. I have now created this one is we're going to use later in a minute, but this is now my listing file of what I just made. So I should be able to see some assembly language instructions in here, and here they are. They're the 32-bit format like we looked at, where it shows up how it, constructs those commands based upon the instruction that you want to do and the operands that you're passing into it. And so there's one more little bit of complexity here is to make the executable from the object module. We have a thing called a linker. So LD is the linker command, and the output from the linker would just be called add, and then the input to that would be add.o. And so if I run that, now that made an executable here, which if I run it, add, nothing happens, but at least it ran and it didn't crash. So now we could go just a little bit further forward on this. And so if I open that file back up, it would be really nice in my adding program if I could print something. So what I'm going to do, and I'm going to make this just a little bit bigger here and go over the other window for a minute, is in order to, and don't matter where all this comes from, but I'm going to say this is print a character, print to standard out is, in Linux, where this console is considered standard out. So what I want to do is I want to move some stuff into some registers. So into the, where I want to print a character, into the X0 register is where I am going to want to move a number 1 character, a value of 1, because that is a file descriptor of standard out. And then I'm going to want to move into, I'm going to want to load a register, X1, and then X1 is going to want to be the address of a buffer. Let's call that out buffer. And so I need to create that buffer. So I'm going to come down here for a minute and I'm going to say out buffer colon. And so I'm defining a label. And then I'm going to go ASCII, and I'm going to give it, say, an A character. Put that in a quote like that. And then just so it isn't just sitting there as one character all by itself, I'm going to define some bytes and just put, 0 in them afterwards, just so there's some bytes there a little bit past our A character. So now this is the address of the output buffer. And then this is going to be a move. Then in the X2 register is where I would want to tell it how many characters are you going to want to print. And so in this case, it's going to be 1. So this is count of characters. And then I need to tell it X8, like down here, this is where I told it, X8, I'd like to exit the program. I'm going to tell it here that I would like to do a read, and the code for that, and don't mind the fact that I'm just kind of, putting these in manually, would be a 64. So this is the operating system code for read. So now I've got a file descriptor of standard out. I've got an address of a buffer. I got 1 character. The only thing left here is to do my system call, which again says, call the OS. It's going to say, put this request out and say, as soon as you can, go do this for me, and I will wait until you return back a value to me. And so to do the call, these registers contain some information. So the operating system is going to look at these registers. It's going to go do some stuff. And then when it's done, it's going to return back. So when it returns, so we can say on return, the X0 register will be error if exist. And error codes are usually negative on that. So if I have done this right, now I have my program so far has 2 operating system calls in assembly language. So using these, high-level commands, I took one of my 30 registers and I put a number, I put a buffer address, I put a count, and I put a code number to send the operating system. So now this first has to be assembled, and we'll make sure whether or not we had any problems, and we can look at the add.list. And so now we see there's some more codes, some more actual machine codes being generated in here in order to do this program. But I need to, because it's an object module, I need to create this executable. And so if I hop back here, I can find that. And so now when I type my --add, now I get my letter A. It's a little hard to see. It's over here in the corner, but it did print out. If we wanted to make that a little bit clearer back in the program, we could go back in here and we could say, well, down here in the buffer, I could add another ASCII, and then I could put, it could be in the same line. I'm just putting it here to be clear. \n it means a carriage return or end of line character. Or I could put byte, and then in hexadecimal, I could do 0x 0a, and that would be a end of line character. Either of those would produce in the same result. But right now, I'm only printing one character, so if I up this to say I'm going to print 2 characters, then it will go to this buffer address, and it will print the A, and then it will print an end-of-line character, and you'll see that those are the same in a minute. So now, it will get a little tedious to come down here all the time and try to redo these assembler commands. So one thing you can do is you can, copy these out, and then you can create what's called a makefile. So then you can nano makefile. And so for the assembler part of this is my assembler command, same as I had it before. But what I would want to do here is I would want to say, I'm going to make an add.o module as a result of this. And what I want to do is I want to update this whenever add.s changes. So this first line here just says, for this output file, whenever the modify date is high enough on this file here, this add.s, then I should redo this again. So if I just type make, now I've run that command and I've made my listing module. And if I cat my add.list, now I can see down here that this is my letter A in hexadecimal, but now I have my end-of-line character by this method, and you can see they're the same. But it's only going to print 2 characters, but either one of those would optionally have been the same end-of-line character. But I can't run it yet. If I type run it, it's still just printing the letter A out. I don't have my carriage return because I haven't relinked it yet. So if I go back and I find my previous linker command, I can just copy that out and add it to the make file. So now in my make file, I want to put my linker command, but I want to make that conditional also. So the executable output, will need to be relinked whenever there's a change in the output module. So just remind you, changes in this source file here will cause this source file to be recompiled into the output module. If this output module is then recompiled, this becomes a dependency, and so the linker will need to redo it as well. So if I save that, and then I type make, now I can run it, which is add, and now I have a letter A and a carriage return. So I'm going to take just a moment here and type my program out and reflect on what we have so far, because we have we've told a global starting point. We've told a small set of instructions which is going to print a character, and we have a buffer set up with this character in it, and then we have an exit to the operating system, and then that's being compiled into a file. That file contains binary over there. Just so that you can see it, you can use a debugger, and that's called GDB, and you can put in this add program into it, and then if you do, you could list some of the assembly language instructions out. I don't want to go into too much, but say I wanted to list 10 of them, the full 64-bit sized with hexadecimal starting at start, then this is, and then it went as far as it could, and then it couldn't go any further. If you wanted to down those to the 32-bit size, now you can see them. These are instructions initially, so they would be there. And then if you wanted to list the program, you could list this. We go all the way down to where this like letter A is, and so we could actually see those if we wanted to go further down. So it allows us to go down and disassemble it as well. So disassemble from start, then it looks a little different because this is coming back from the machine code. So now we've generated a little assembly language. So here's our number for, go print a character. And then here's the count of how many we want to print. Here's the address of my buffer that I'm printing from. But this is the code. This is the code that would be like in memory, that the address is where you would go look for that code. And so this is where, when people look at, like for vulnerabilities in software, they go through these addresses one by one, and then they try to backwards track into these, and this is where they would look for issues. So I don't want to get too much into the debugger right now, but just let you know that that exists. So going back to the add program, and so I'm now in my add.s, I have this address in this buffer down here. This A is being printed. What if we put a different letter into the buffer? So we could come up here and we could say, how would we do that? Well, if we were to load the one of the registers, and there's 32 of them, I'm just going to pick X1. And then if I want to get the address of that buffer, then that would be, the equal sign means that out buffer. And so we're going to get the address of buffer. And then if we wanted to put something else into it, we could use one more register. And so we could move into the X0 register. And then I am going to say put the letter Z, Z for everybody in Europe. And now that should be able to then store register X0. Actually, that's not going to work. I gotta use a 32-bit for that. I want to store the byte into the location being referenced by the X1 register. So the X1 register is the address of the buffer. The W0, that's X0 is 64-bit. This just goes down to 32-bit because of the way the instructions work. You need to fit within the 32-bit. And then so this will then take that value Z, store it into X1, which X1 should then replace this with the letter Z, and there it should be. So now I should just need to type make, and it made correctly. So then I can run it, /add, and I have a segmentation fault. And so you would say, what does that mean? That means generally you tried to address something in memory that you couldn't. And you go back to the program and you say, I must have made a mistake here somewhere. But in fact, it's not really a coding mistake because all we added was this. And you could say, well, yes, that's the address of it. Yes, that's moving the character. And this all looks fine. But the problem is I have been very simple in how I've been writing this program. And it's assuming that everything in this program is code. And now we're trying to change some values down here that aren't in the code. So one of the things I need to do is I need to come down here and I need to tell it that this section down here is data. And so this can be modified by program. And it is initialized data with something already in it. And so if I'm gonna do that, I've got to come up here and I've got to say this is text. And so text doesn't mean text like typing, but text means this is immutable. Nothing should be changing your program. So if there is some security issue somewhere, buffers are being overrun or something like that, you saw that in the program section, we were not allowed to change things once it's been compiled, and that's sort of a security feature. So now this data down here is going to say, all right, the stuff in the data segment can be modified. It's legal to do that. And so now it should run. And so now if I make it and then I run it, and now it ran, and see, instead of an A, I have a Z printed out. So I'm getting close. I've now, have a ability to print characters. It's looking really good. I would like to shift gears here just for a minute and talk about adding a number. So, and I'm just going to bring the PowerPoint over without making it full screen because I kind of want to have two things open at the same time. So remember, every one of these bytes or words or 32-bit word or 64-bit word, it can have a number in it, it can have text in it, it can have various things in it, it can have instructions in it. If we're looking at one byte, I'm way up here at the top, where it's up here. This byte is part of one of these 64-bit words. It's the first one. That's where the letter Z is right now. But what if we wanted to have a number? Well, numbers are like 1, 2, 3, 4, 5. If it's in hexadecimal, you'd add them up based upon the bits. So you could, by knowing what bits are ones or zeros, you could figure that out. But what about text? And so this is, I guess this may be review for everybody, or I don't know if it is or not. But if you have a number, that would be here on the left. And so these are binary. And so 0 is all zeros, and then 1, and then 2 is 10, and then 11, and 100, and 101, and 102, and so on. So these are base 10 numbers counting up from 0 to 9, and this is what they look like in hexadecimal, and this is what they look like in binary. But over here, and again, this is ASCII. ASCII is 8 bits. There's also Unicode, which can be 16 bits or more, and so on. But ASCII digits are sort of like a subset of Unicode, and so I can deal with, going back to my previous slide, I can up here in this corner, I can keep one 8-bit register for using a number, and I can use that same one for using a digit of text. The difference is that for these to be digits, they have this hexadecimal 3 on the front, or in binary, the 0011, the first 4 bits of it are always 0411. The last 4 pretty much follow what's over here. So one thing you could see is I could go back and, as long as I'm a digit 0 to 9, I can go back and forth, because over here, I don't know if I can edit it, I can just strip these off, and then I'll have this number over here on this side. Or if I'm over on this side, I could OR these bits into it. So if I have either or of these together, then I would go back to one of these values by going back and forth from each other. So that means I could actually, kind of print a number simply by doing this OR command down here. So if I were to go back to my program here, then I can come down to, I want to be up here where I'm putting this into my out buffer. So right now I don't want to, I'm going to get rid of this Z here for a minute. And so I have a instruction here which is going to store character in W0 to the output buffer. And this little, assembly language down here. But I don't have anything in the W0 down here yet. So let's say that I had, and I'm going to move a binary number in the W0 register that was 3. We were adding 3 and 4 before. So now the W0 register, if I tried to print 3, 3 is like, 1 is like a control A, 2 is a control B. It's not going to be a printable character. But what I could do, just like if I can kind of get these on the same screen here, if I can kind of, OR these together, there's my number 3 is on the screen there. What I would want to do would be to OR, and now the output is going to go into W0. I'm going to take the contents of W0 that I'm starting with, and I'm going to OR it against, and I could put this 2 different ways. One way would simply be to put the hexadecimal 0x30, that's my value up here with nothing in it. And if I do this, then my W0 register should now contain the digit 3, because I've got the digit 3 and I've got that digit there. So if I save that, and I'm going to kind of combine a couple things together here. If the make has no error, then I can just go ahead and, the and means if there's no error, then continue on to the next command. And so it printed the number 3 out. just so you can see it, if I, if I were to come down here and make that a 5 and then run it, I've now got the number 5 printing out. So, okay, I can take a binary number and I can convert it to an ASCII digit, and then I can send it to the call to the operating system, which is going to print the character. Here's a print the character, and then it will exit the program. So I should be able to do an addition. That was my goal, was to do an addition. So if I copy these 2 lines and I put 3 into the W0 register, then instead of moving them together, I'm going to add. And so I need 2 registers for that. So I'm going to move the immediate value 3 into the W0 register. I'm going to take the W0 register, I'm going to add the immediate value of 5, and then I'm going to put that, actually let's put, to be consistent, let's put 4 because that's what we were using in all the other examples. And then I'm going to convert it to an ASCII character by ORing it against this 3-0. So if I do that, now I'm getting the digit 7, which is 3 plus 4. You say, well, that's really cool. You know, you just, you know, you were able to write a little program that took the digit, loaded a register of the processor with 3, took an immediate value of 4 and added it to it. And by the way, I can look at this listening file over here, and I can see that this is where I put my value 3 in, and this is where I added, you can't decode what these are, but this is where the 4 added in. And you could say, could I actually go look at the debugger and see that? So if I go to the debug GDB and do /add, I should be able, so disassemble start, and I should have, here's my 3, it deassembled it back out. Here's my 4 being added to it. Here's my ORing, putting it back in. You see my system calls down there. And so the debugger is able to go ahead and see that as well. You say, well, that was fine, but what I really want to do here is to be able to have some user input. And so what can you do to get me some of that instead? And so let's just, I'm going to just put a comment in front of this this one here. So I got a comment on this one. So this one is convert binary to ASCII. Then we'll get rid of the other one in a minute. If I come down here to my printing call and I copy it, I'm going to actually copy it this way. Then I can come up here to the start of the program where I just removed out that other command, actually it'd be here. And I can take out my sort of copy buffer. Then I can say this is going to be input character. So it's going to be very similar, except that one of the things that I'm going to want to do, sorry, I keep missing that highlighting color. One of the things that I'm going to want to do is I'm not going to want to use the out buffer. I'm going to want to make a new in buffer. I'll just call it in buffer. So I go down here to the end where my out buffer is. I need to define an in buffer, and I am going to come along and say that in the case of this buffer down here, I'm just going to want to skip 255 or 256 bytes. So that's just going to say I'm going to reserve some space. So another thing is that because these are kind of, you don't know what length all these ones are in front of it, if I wanted to make sure this was aligned evenly, you might want to do that to make it easy to look at in the debugger. You could say align 4. So like 1 would align to a byte, 2 would align to 16 bits, 3 would align to 32. So this would say if my code is kind of out of alignment, this would kind of kick it back in. And in fact, if if I wasn't sure of this one, I could put, one here just to make sure that at the end of the program, if there was more stuff coming in other modules, it was aligned as well. So that's just kind of an alignment command. So now up here, I've got a in buffer. Right now, I want to read, I'm only going to read one character because I'm a little limited here. This is just working at digit 0 to 9. And my call here would be a 63, means read. So this is going to be standard in, address of the input buffer, count of the characters is 1, and this would be like max. If you put more, I could put more. Actually, let's put more. Let's just say there's 10 there. We're only going to use the first one, so it'd be up to 10. And then this is going to open the operating system for read and call the OS. The result will come back from this as the X0 register will have count of the characters read or error code, and the X1 will be address pointer to buffer. So if it goes well, then that should be there. So now the W and the X registers are the same, except I'm going to go back here for a sec. So the W register would refer at the bottom here to this full 64-bit word, and that's where the system call is going to be dealing. But we're only going to look at the lower 32 bits. So whereas this goes to bit 63, we're only going to go up to bit 31, and we're just going to, the W just refers to half of a word, but the word is still there. So what I would want to do here is I would want to, now that value that is in the X1 pointer, I need to put it in a register. So I'm just going to, there's 30 of them, I'm just going to pick another one. So I am going to load register, say W10 with and now my X1 register, and so we're going to get the character in the address in X1, of the buffer. So once I have that character there, now I got to come back over to here. That character is going to have these extra bits on the top, and I want to get rid of those. So where I did a OR down here, I OR'd it to turn it into ASCII. On the input side, I need to do the opposite. So up here, I am going to and then my W10 register, I'm going to store it in the W10, I'm going to start with the W10, and I'm going to AND it with the immediate value of 0F. So 0F would be like, I'll just put it here. So 0F equals 0000111 in binary. So that will come over here and it will strip these away because they're all zeros against this half. So neither of them will be both 1 and the other one 1. But on the other hand, all of them are 1 on this half, so whatever's here will equal through, and that's referred to as masking. So if this is right, I should have a W10 register which has a character in it. The character is going to be stripped down into binary in that register there. And then if I wanted to, and I'm just going to come down here and say, I want to add the W10 register plus the value 4 into W0, and then that should work. So if I do this and see if I have any mistakes here, I want to make and run. I have no mistakes. It's waiting for input. So if I type a 3, I now got a 7. And so just to remind you what we're doing here, I'm going to apologize for those colors, then we already have a 4 that we're adding. So we brought in some character from the keyboard. And so coming down here, if I run this, and it's up to date, so it didn't need to make it again. If I give it a 1, it's going to give me a 5. If I run it and I give it a 2, it's going to give me a 6. If I run it and I give it a 4, or a 5, it's going to give me a 9. What I can't do is give something higher than 9, because then this business of forming the characters is going to overflow out the top. So if I go and I try to give it a 6, then I'm going to get a colon. And if I try to give it a 7, and then I'm going to get a semicolon and so on, because I've gone into different characters that aren't 0 through 9. But it'll work up till that amount of characters. So you say, like, well, you could just, do that for both of them, so you don't have to have one of them prefixed. And you say, sure, no problem. So what I would do in that case is I would come up here, and I could just, so what I've got here is I got from here to here is putting a character into the W10 register. So if I just duplicate that and put that in here, that's not necessarily a good way to do that. So now this is going to, let's just say, read other character. Then when I get to the point down here, I'm going to want to put that character into a different register. So I'm going to put this into register 11. So now up here, we're putting it in register 10. We're going to get another one and put it in register 10. So now down here, I'm going to want to have W11 be my addition. So my add is now going to, the add is going to store it in W0, but it's going to take W10 and W11 registers, add them together, and then that will be turned back in. So you come in with an ASCII character, this and turns it to binary, then we add them together, and then this or puts it back into ASCII again so that we can see the printed value. So if that works, then I should be able to now type 2. So we could say like 3 plus 4 is 7. And do it again as 2, and 2 is 4. And so now we have a adding routine. And just to go one little step further, what I want to do here is I want to say, yeah, but you've got all this code in here twice. Why in the world would you do that? And you say, like, okay, well, what if we took this first part out? Let's just take it out altogether. And then I'm going to go to the very end here, not in my data segment. I'm going to put a little divider here. So this is like the divider to my data segment. But here at the bottom, now once I hit this, system call on this line here, you'll never go further than that. It'll stop here because that will return you back to the operating system. So we could say something like get input, doesn't matter what you call it. And then here is where I could, put all this input character getting routine in here. So now if we go to this address, this will do these steps, getting a character from the operating system. And then we would think we could just come here and do a return. You think you can, but you're going to get into some problems doing that. So back up in my original location, I'll come back to there in a minute. What did I call that? I called that get input. So where I deleted all the stuff here at the beginning, I would want to, and then BL is the code for, do a subroutine call to there. I would want to get input, and this is going to return count/error in x0 and address in x1. So I'm not really giving that function anything, but once I've done that call, then I can go right ahead and use these, and so I don't really need to duplicate it twice. If I wanted to do both of them, I'm going to leave the other one in there just so you can see it. But you could do as many of them as you want. Is now you just have one subroutine call, and then you're dealing with your register in x10, and then you see how this stuff down here matches this stuff up here. It's just a simple way to do it. The problem is, there's registers here that I'm doing things with. And then I'm coming down to this call. Sorry, get it on the screen. And I'm doing things with several. I got 0, 1, 2, 8. And what if somewhere else in the program had important data stored in those registers and I started assigning them to things? So one of the things you got to do is you should really save your registers. I don't really need to save 0 and 1 because 0 and 1 is going to have something in them when I send it back. So there's no point to really save those two. So I'll do it here up front. And because this is reduced instruction set, it doesn't really have a pop and a push and a pop like a regular operating system would have. So what I need to do is I need to make my stack pointer, store my stack pointer into the previous value of my stack pointer, and then I'm going to subtract 64 bytes from the stack pointer, and that is make room for 8 words on stack. And then typically you would store the X30 register. That's the return address for this return statement down here, onto the stack pointer at offset 0. And then you would store X29. I don't have anything in X29 right now, but it's kind of a common practice to store that one too. And because these are 8 bytes apiece, come back here. So these are 8 bytes down here at the bottom. The word is 8 bytes, so I got to go up by 8 every time I do this. And so now, if I do want to save my X2 and I want to save my X8, because they may have important things in them from somewhere else in the program. So then that would be at offset 16 and offset 24, so 0, 8, 16, 24. But I have room for 8, but I'm putting 4 onto there. So now these need to be put back when I'm done. So here, before I return, I need to, first, to get this one out of there, if I subtracted them at the beginning, then I need to add them back at the end. So I moved a stack pointer down by, 64. So now I'm going to simply add instead, and that puts it back to where it was. So these are going to be load registered. Actually, these are going to be load registers, load register, and load register. So what we stored before when we started, we're going to put the original value back. And the important one would be this X30, because when we call the operating system, that there might be subroutines in the operating system that do returns. And this return statement here, that's the address that's going to return back to. So now, I know it sounds complicated, but I've got a function here. I saved my registers. I've used my registers as I did before, and then I've restored my registers back and did a return. And that whole thing here at the top is coming in here at this get input function, and I really don't need this one up here anymore. So I'm calling a subroutine with my registers protected. I'm returning back a number. Then I'm getting the next character the long way, and then I'm forming it back into a ASCII character from the added together. I'm then my output buffer. I print my output buffer. I exit to the operating system, and that should, using that subroutine, if I don't have any typographic errors in there, I can type 3, 4, and there's my 7, and there it is. So what all did we cover here? And I think this is sort of a good place to stop, and I'm going to bring up my program. Like one more small little detail here. Actually, go out for a minute. This is a Raspberry Pi 4, and it has the 64-bit version of the operating system on it. So if I type LSCPU, my architecture is the AArch64. And by the way, this won't compile without that. But it's a Cortex A72. And so how did the compiler know that? Well, it figured it out from some kind of default system values that are in the system. But it would really be a good practice to specify that. So if I come up here to the top, I could say that there is a .arch, and that arch right now is off that other one. That would be the ARM v8A, and the other one is the .cpu, and that is going to be the Cortex A72. The Raspberry Pi 3 has a Cortex A53. I think you'll find you could put either one. They probably don't make any difference for what we're doing here. But this just simply makes the assembler and compiler aware that, this isn't, some other version of assembly language program. It's assumed it because that's how the operating system was compiled, but we might want to, for a specific purpose, be a little more general. So just to review through the program, we've got a little bit of stuff just to show you that works. So if I run it here, I can do my 1, 2, and I got 3. So going back into the program, I've told it that I have some specific architecture. I need a starting point for the linker that's defined here and is made global. And I have a section here, a segment to put the code into. The executable code is going to call a subroutine to read the first character. It's then going to change it from ASCII into binary and put it in the W10 register. Then I'm going to manually call the operating system call again, although I could have used my subroutine. I'm going to put that one in the W11 register, and then I'm going to add the W11 register to the W10 register and store it in W0. And then I'm going to use the OR to change it back into ASCII. And then I'm going to store that character back into the output character buffer at the end. I'm going to call this system call to print the character. And then I'm going to exit the operating system. And I have my subroutine here with save the registers, do my call, and then restore the registers. And then down here at the bottom, I've got a little section for my text buffer data. And then in here, I've got my in buffer data. And just because it probably would be a good thing to do up here is where I'm doing this OR line, like I did down below, I could alternately have simply told it to use the 0 digit. And so if I put that in there, this would be equivalent because over here, the 0 digit here, 30 hex, is equivalent to this. You see the two are exactly the same. And so just so you could have it on here, and I'll put a little note here that says these two are the same. One of them is using the digit and one of them is not. So since I changed that, let's just show that it still works. And I can do 1 and 5 is 6 and it still works. So that's basically it. The reason that I kind of wanted to do this, and nobody wants to just add one digit, but you know, I had a lot of feedback on the program where I calculated pi to 1,000,000 digits that what I said was a little too complicated. And so this is just a quick look at assembly language. But what I have here that is exactly analogous to the other program is I have a routine here at the end that can I get somewhere. There we go. I have a routine here that can read the keyboard. And if I want to have a sort of advanced calculator and some simple commands, as long as I can get the characters read from the keyboard, come in on that buffer, I can interpret commands. I can be a calculator. I could say like, you know, calculate sine, or I could say do a square root or something, because I could just, you know, go through and do if statements sort of on those commands. I have a section a little higher up in the where am I here? In the code that is not up, lost my place, where I'm doing my addition. So after I read my variables in, I'm now adding them. So that's like a math function. So to calculate pi, you need to do adding and subtracting and multiplying and dividing and things like that. So that's basically what it is going through and doing a lot of multiplying and adding and summing up long series of numbers that you've done that to. So I've got my input reading. I've now done some arithmetic, and that's what the program does. A lot more of it, but it's just assembly language arithmetic. And then I converted it back to base 10 for output. So this is just a like base 10 conversion back. And then I printed it to the console out. And that's basically what the other program did to calculate pi. It can get input that works as a calculator. It has arithmetic functions, just like this adding statement. And then it prints it out, just like we do down here where we print it to standard out. And that's the program. So if you look at the sort of micro version of this, this is all assembly language. There are no libraries being used on anything here, similar to the other ones. And I know I'm a little bit, you know, cryptic because you can go through and you can give these names and, you know, things like that to make it a little easier to read. But this is the pure machine code. If you're coding like this, you are literally one-to-one, you know, with the processor in the Raspberry Pi. In other words, you can do any instruction allowed, you know, for a program to run that it can possibly do. And the nice thing about the Raspberry Pi, you can see these are pretty simple. You know, I had like loads and moves and add, store byte or store word. That was basically, I only had like, you know, 8 or 10 instructions here, and that was it. You don't need a lot more than that. And so the assembly language in the RISC processor on a Raspberry Pi is pretty easy to just go in and start learning like that. And so hopefully this clarifies a little bit about what the big because the other presentation was like, you know, 2 hours long talking all about assembly language. But if it didn't make sense, hopefully these examples of this code will exactly make sense. And I'll see if I could pop this thing on GitHub just so you'd have it to go look at.